I'm Adam from RFOXiA, from our real lab. Today we're answering why a supercapacitor can fully charge in under 5 minutes when a battery with equivalent stored energy would take hours, and why that difference is physics, not marketing. Enjoy our new soundtrack at the end of the video. Let me start with a statement that the battery industry has spent 40 years not making particularly clear. Charge time is not determined by how much energy a device stores. Charge time is determined by the chemistry or absence of chemistry involved in storing that energy. These are different things. They are related in batteries. They are not related in supercapacitors. Once you understand that distinction, the 5-minute charge time stops sounding like a marketing claim and starts sounding like the obvious consequence of the physics. A lithium-ion cell charges slowly for several compounding reasons. First, the storage mechanism is electrochemical. Lithium ions must physically migrate through an electrolyte, intercalate into a graphite anode structure, and settle into lattice positions. This is not an instantaneous process. The ions move at a rate limited by diffusion coefficients, temperature, and the structural integrity of the electrode material itself. Push ions in faster than the lattice can accept them, and you get lithium plating, metallic lithium deposited on the anode surface rather than intercalated into it. Lithium plating is a safety problem. It creates dendrites. Dendrites grow across the separator. You know how that story ends. Second, the charge acceptance of a lithium cell drops dramatically as the cell approaches full charge. The constant current phase that begins a charge cycle gives way to a constant voltage phase where current tapers, sometimes for longer than the initial CC phase. This is not a charger limitation. It is the cell protecting itself from overvoltage damage to the cathode. You cannot simply increase current to speed this up. The cell will not accept it without accelerated degradation. Third, the heat generated during fast charging in lithium cells is not merely a thermal management inconvenience, it is a fundamental consequence of internal resistance under high current. Power equals current squared times resistance. If you double the charge current, you quadruple the heat generated inside the cell. This is why you cannot fast charge a lithium pouch cell with a 10 amp current without dedicated thermal management and real engineering attention to the cell's C-rate ratings. Now, a supercapacitor does not do any of this. A supercapacitor stores charge electrostatically. Ions from the electrolyte adsorb onto the surface of high surface area electrode material, forming a double layer. No chemical reaction, no ion intercalation, no phase change, no lattice site occupation. The storage mechanism is purely electrostatic, and electrostatic charge transfer is not rate limited by diffusion in the same way electrochemical processes are. When you apply voltage across a supercapacitor, charge accumulates. When you remove that voltage, it stops. The speed of this process is governed primarily by the RC time constant of the circuit, the product of resistance and capacitance, not by ion migration dynamics. This is why the charge curve of a supercapacitor looks the way it does. In a simple RC circuit, voltage across the capacitor rises exponentially toward the supply voltage. Theoretically, it reaches approximately 63% of full charge in one time constant, 86% in 2, 95% in 3. For a supercapacitor with a low equivalent series resistance, what engineers call ESR, and a high current source, that time constant can be very short, minutes, not hours. The 1100 farad supercapacitor in the Multinav Pro Plus Power program kit charges at 4 volts, accepting 10 amps from the included 12 volt 5 amp adapter through the onboard charging circuit. Let me put the stored energy in numbers because people underestimate what 8,800 joules represents in practice. A joule is a watt second. 8,800 joules delivered at the roughly 3.3 volt operating voltage of the modules represents enough energy to sustain continuous operation at low to moderate current draw for well over a working day in normal field deployment. The BLE module, GNSS module, and sensor module together draw modestly. The supercapacitor supplies that draw without chemistry, without degradation cycles, without the capacity fade that accumulates in a lithium cell across hundreds of charge-discharge events. There is something I want to address directly because I have seen it come up. People hear 5-minute charge time and assume it must be delivering that energy at a dangerously high rate, that there must be a catch, a compromise, a heat problem they are not being told about. This intuition comes from battery experience. It does not apply here. The reason supercapacitors can accept high charge currents without significant thermal concern is precisely the ESR. The internal resistance is low, sometimes a fraction of an ohm for high quality electrodes. Low resistance means the I2R heating is manageable even at elevated currents. The electrostatic storage mechanism does not generate the exothermic reaction heat that electrochemical intercalation can. You are not forcing a chemical process faster than it wants to go. You are filling a container that was designed to fill quickly. Is there a trade-off? Yes, there is always a trade-off. Supercapacitors have lower energy density than lithium. That is the physics behind why the charge time is what it is. Now let me show you the actual hardware, what this kit contains and how it connects to the rest of the system. This is the supercapacitor module itself, 1100 farads storing 8800 joules at 4 volts. What you are looking at is the reason the charge time conversation changes entirely. No electrochemical intercalation, no lithium plating risk, no capacity fade over hundreds of cycles. Electrostatic storage accepts current quickly because it is not fighting a chemical process. This module is the physical consequence of everything we just discussed, and it powers your entire stack for a full working day. This is the high power charging adapter, 12 volts, 5 amps input, delivering 4 volts at 10 amps to the supercapacitor through the onboard charging circuit. The reason this works safely at this current in under 5 minutes is the low equivalent series resistance of the supercapacitor electrode. I2R heating stays manageable because the resistance is a fraction of what you would find in a lithium cell. Plug this in at the start of a field session. 5 minutes later, you have a full day of operation. This is what full day operation looks like in practice. The power program kit supplies the BLE module, the GNSS module, and the sensors module simultaneously, the complete multi-nav Pro Plus stack from a single supercapacitor charge. The combined draw of these three modules is low enough that 8800 joules covers a real working day in the field. No battery swaps, no mid-session charging interruptions, no degraded capacity from the 100th charge cycle. The supercapacitor does not care how many times you have charged it. This is the integrated ST-Link programmer. It sits in the same kit as the power supply because programming and power are not separate problems in field hardware development. They are the same problem. When you need to push a firmware update in the field, the power system that runs your modules also powers the programming interface. The ST-Link handles firmware flashing and live debugging for the BLE module through a flat ribbon cable connection with no additional bench equipment required. This is the complete connectivity hardware included in the kit. Flat ribbon cables and all interface connectors needed to tie the BLE module, the power module, and the programmer together. Nothing is left out, nothing needs to be sourced separately. The flat ribbon format keeps the stack compact for field enclosures and drone mounting. The reason this matters in the context of charge time is simple. A system that charges in 5 minutes and deploys in 2 minutes is a system that spends its time working, not waiting. Mass. For applications where you need to carry enormous energy reserves in a small form factor, batteries still win. But for field hardware, where a charging source is available at the start of a session, where you need rapid turnaround, where you need a power system that does not degrade measurably over its operating life, and where you are powering electronics rather than motors, the calculus changes. The 5-minute charge is not a trick. It is what happens when you stop fighting the chemistry and work with a mechanism that does not require it.
5 minutes on the dock, full charge and I'm unlocked. Capacitors hold the line while batteries fall behind. Field ready every time, no waiting, no decline. Plug it in, fire it up, one connection, that's enough. Never stop, never drain. 5 minutes and I'm back again. Charge to full, run all day. SWT lights the way. Connect the at the SWD pins. The programming begins. Flash the firm on clean. The sharpest stack you've seen. BL breathing live. All sensors locked and primed. From bench to open sky, nothing slows this drive. Supercapacitor surge, instant energy in reserve. No cell degradation, every charge is full and pure. ST-Link ready, write the code and push to hardware. Field deployment, no excuses, always there. Never stop, never train. 5 minutes and I'm back again. Charge the full, run all day. SWT lights the way. Never stop, never train. 5 minutes and I'm back again. Charge the full, run all day. SWT lights the way. This circuit was designed to shine.
WD. Full power.